Another extraordinary quasar, even more dazzling than TON 618 in sheer radiance, is J05294351, currently recognized as the brightest known object in the observable universe. Discovered relatively recently using data from the European Southern Observatory, this quasar has astounded astronomers not just with its luminosity, but with what it reveals about black hole accretion in the early cosmos. J05294351 is located over 12 billion light-years away, meaning we observe it as it appeared when the universe was less than 2 billion years old. Despite its great distance, it outshines everything else known, galaxies, clusters, even other quasars, emitting more than 500 trillion times the luminosity of the Sun. This staggering output makes it a cosmic lighthouse visible across much of the observable universe. At its heart lies a black hole growing at an extraordinary pace. Estimates suggest it gains the equivalent of one sun's mass every day, an accretion rate that pushes the limits of known physics. The black hole's mass is already tens of billions of times that of the Sun, yet it continues to feed furiously, converting matter into radiation with record-breaking efficiency. The source of this power is a vast accretion disk surrounding the black hole, glowing white-hot as gravitational energy is transformed into radiation. This disk likely spans several light-years in diameter and is spinning at relativistic speeds, creating intense friction and magnetic turbulence. The result is a flood of high-energy light, blasting out from the quasar's core in all directions. What makes J05294351 especially fascinating is how its brightness challenges our assumptions about the Eddington limit, the theoretical maximum brightness a black hole can reach without blowing away its fuel. Somehow, this quasar appears to sidestep those constraints, raising new questions about radiation pressure, disk geometry, and even possible changes in physical laws under extreme conditions. The unprecedented luminosity of J05294351 makes it invaluable for testing astrophysical theories about black hole growth and the physics of extreme gravity environments. It represents a cosmic scenario that pushes standard accretion models to their theoretical breaking point, compelling astronomers to refine or entirely rethink classical assumptions about matter-energy conversion near event horizons. One pivotal aspect is the quasar's apparent super-Eddington luminosity, exceeding the theoretical Eddington limit, the balance between gravitational pull and outward radiation pressure. This paradox implies unusual physical conditions, such as anisotropic radiation, radiation not emitted uniformly, or exceptionally rapid accretion flows. The super-Eddington accretion may result from thick, magnetized accretion disks, possibly supported by intense magnetic fields and turbulent viscosity far beyond typical predictions. Detailed spectroscopic studies of J05294351 have revealed prominent emission lines, characteristic of extraordinarily hot, ionized gas clouds orbiting at velocities approaching several thousand kilometers per second. Analysis of these lines provides critical clues about the chemical enrichment and metallicity in early cosmic epochs, implying that heavy element synthesis processes occurred remarkably rapidly after the Big Bang, much sooner than traditional galaxy formation models suggest. Moreover, the intense ultraviolet, UV, and X-ray radiation emanating from J05294351 impacts its surrounding galactic environment profoundly. This phenomenon, known as quasar feedback, occurs when powerful radiative and kinetic winds driven by the black hole's accretion disk expel gas from the host galaxy at tremendous speeds, altering star formation histories and ultimately influencing galactic evolution on massive scales. Astronomers also utilize quasars like J05294351 as cosmological beacons, probing intervening cosmic structures. The extremely bright radiation emitted from this object passes through intergalactic space for over 12 billion years, encountering gas clouds, filaments, and dark matter halos. As a result, the absorption lines detected in the quasar spectrum, known as the Lyman alpha forest, serve as a cosmic chronicle, revealing the evolution of baryonic matter and cosmic reionization processes at different epochs. Additionally, J0529 4351 aids astronomers in measuring cosmological distances and refining parameters such as the Hubble constant and dark energy density. Variability studies, exploiting the quasar's intrinsic brightness fluctuations, allow precise timing measurements and can yield independent constraints on fundamental cosmological constants. Further investigation using next-generation telescopes like the James Webb Space Telescope, JWST, Extremely Large Telescope, ELT, and future space-based X-ray observatories will likely provide more precise data. These facilities promise deeper insights into the quasar's host galaxy, currently obscured by intense central emission, as well as detailed maps of the immediate environment surrounding the supermassive black hole. Through gravitational lensing effects, astronomers might also discover previously undetectable structures, including small-scale dark matter concentrations or hidden dwarf galaxies along our line of sight. Such lensing phenomena, magnified and illuminated by the exceptional brilliance of J0529 4351, could help astronomers resolve current tensions in galaxy formation theory and dark matter distribution models. J0529 4351 thus serves as more than an extraordinary cosmic lighthouse, it is also a unique astrophysical laboratory, capable of testing general relativity's predictions in ultra-strong gravitational fields. For example, studies of iron K-alpha lines emitted from the inner regions of its accretion disk may reveal frame-dragging effects, a phenomenon predicted by Einstein's theory, where spacetime itself is twisted by the rotation of such an enormous mass. As observations become increasingly precise, J0529 4351 may ultimately allow tests of more speculative physics theories as well, including quantum gravity models or alternative theories addressing black hole singularities and information paradoxes. Such research may eventually bridge the gap between classical astrophysics, general relativity, and quantum mechanics. Continuing studies of this extraordinary luminous quasar have implications extending even into fundamental cosmological puzzles, including cosmic inflation and early structure formation. The sheer intensity of its radiation not only reveals processes in extreme gravitational and energetic regimes but also enables high-resolution spectroscopy and polarimetry, providing a unique glimpse into the geometry and dynamics of the immediate surroundings of the supermassive black hole. One intriguing aspect of such hyperluminous quasars is their potential role in cosmic reionization, the epoch when neutral hydrogen gas filling the universe became ionized. The immense ultraviolet and X-ray output of this celestial beacon indicates that similar superbright quasars, though rare, may have significantly contributed to the reionization process, accelerating the transition from a neutral, opaque universe into the transparent cosmos we observe today. Additionally, the exceptional brightness of this quasar allows astronomers to scrutinize subtle relativistic phenomena predicted by theory but challenging to observe elsewhere. One example is gravitational redshift, where photons emitted deep within the gravitational well of the quasar's black hole lose energy as they escape. Accurate measurements of this redshift could lead to direct tests of general relativity's predictions in the ultra-strong gravitational field regime. The study of spectral variability also yields critical astrophysical insights. Variations in luminosity and spectral lines can reflect instability waves or turbulence in the accretion disk, potentially tied to magnetorotational instability, MRI, a key theoretical mechanism governing angular momentum transport and matter accretion around black holes. By examining how these fluctuations propagate over months and years, astronomers gain insight into the complex physics underlying disk structures and their long-term stability. From an observational standpoint, the enormous brightness of such luminous quasars makes them ideal calibration points for new telescope systems, helping to refine observational methods across electromagnetic wavelengths, from infrared to gamma rays. Their clarity and consistency facilitate instrument characterization and wavelength calibration, thus contributing broadly to improvements in observational astrophysics. Moreover, these hyperluminous objects could indirectly support the detection of gravitational waves from distant merging black hole binaries. The intense radiation emitted might stimulate regions in intergalactic space into fluorescence or ionization, forming environments that could amplify subtle gravitational wave signals or produce detectable electromagnetic counterparts. The quasar's magnetic environment also invites extensive research. High-energy jets and outflows emanating from its accretion disk suggest extraordinarily strong magnetic fields shaped by relativistic plasma dynamics. Studying polarization properties of emitted radiation could thus provide invaluable clues about magnetic field generation mechanisms and the role of magnetically driven winds in energy extraction processes near the black hole's event horizon. Chemically, spectral analysis of hyperluminous quasars frequently reveals a surprisingly high abundance of heavy elements such as iron, magnesium, and silicon, indicating rapid stellar nucleosynthesis in the quasar's host galaxy. Such metal enrichment occurring within the universe's first few billion years forces astronomers to reconsider the timescales and processes involved in early star formation, supernova events, and interstellar medium evolution. Finally, these ultra-bright quasars serve as cosmic distance markers, refining our understanding of universal expansion and the cosmological constant, dark energy. By tracking luminosity fluctuations correlated across different wavelengths, astronomers establish precise standard candles, helping resolve discrepancies between measurements of universal expansion rates derived from cosmic microwave background radiation and those obtained from local distance indicators. Thus, beyond their intrinsic fascination, quasars of such unmatched brilliance fundamentally shape our understanding of physics, cosmology, and galaxy evolution, offering astronomers an extraordinary window into the universe's most energetic, dynamic, and enigmatic processes. The discovery and detailed observation of this extraordinary quasar also provides significant contributions toward modeling supermassive black hole formation. The extreme conditions necessary for such massive growth within limited cosmological timeframes require astronomers to explore unconventional mechanisms, such as direct collapse of massive gas clouds, rapid mergers of primordial black holes, or even exotic scenarios involving dark matter halos that seed rapid black hole accretion. Additionally, advanced simulations of the accretion disks around luminous quasars indicate that relativistic effects such as photon trapping, where radiation produced deep within the disk struggles to escape gravitational pull, may become dominant in such extreme regimes. This photon trapping phenomenon could help explain how these objects surpass the Eddington limit by reducing outward radiation pressure, allowing matter to continue flowing inward at unprecedented rates. Moreover, the quasar's proximity to the cosmic dark ages, an era when galaxies and quasars were just beginning to emerge, makes it a crucial laboratory for understanding conditions shortly after the Big Bang. Its intense emissions serve as backlights illuminating otherwise invisible intergalactic gas, enabling astronomers to reconstruct how early galaxies first assembled from primordial hydrogen and helium gas clouds into structured star-forming systems. Furthermore, observations of such objects enhance theoretical models addressing cosmic dust formation. Despite the intense radiation environment that can evaporate dust grains, these hyperluminous quasars surprisingly host significant dust reservoirs. Investigating how this dust survives, and perhaps even thrives, in proximity to extremely luminous accretion disks challenges current theories of dust grain chemistry, dust shielding, and grain growth processes in turbulent, irradiated regions. Spectropolarimetric studies have also begun unraveling the geometry of these energetic systems. Polarized light measurements allow astronomers to map the orientation of accretion disks, jets, and obscuring structures, known as dusty tori, around supermassive black holes. Such polarization maps enhance understanding of the intrinsic anisotropy in radiation fields, potentially explaining why some quasars achieve extreme brightness despite theoretical luminosity limits. From an astronomical instrumentation perspective, extremely luminous quasars stimulate innovative methods in adaptive optics, interferometry, and space-based telescopy. Efforts to resolve structures surrounding supermassive black holes, including measuring their accretion disk sizes or resolving jets at extremely high resolution, encourage technological advancements crucial to future missions like the Laser Interferometer Space Antenna, LISA, or Very Long Baseline Interferometry, VLBI, arrays. The cosmological implications of observing distant luminous quasars extend even to studies of neutrino astronomy. Hyperluminous accretion events are thought to produce significant neutrino fluxes through high-energy particle collisions near black hole event horizons. Detecting neutrinos associated with these distant quasars would open an entirely new observational window into fundamental astrophysical processes, verifying theoretical models of particle acceleration and radiation physics at extreme energies. Gravitational lensing by such quasars also provides astrophysicists a means to probe intervening dark matter structures invisible through traditional electromagnetic observations. Microlensing by smaller, unseen objects, such as isolated black holes or dense stellar clusters, becomes detectable thanks to the brightness of these quasars, thus informing models of subgalactic-scale dark matter distributions. Finally, the powerful radio and gamma-ray emissions often accompanying ultrabright quasars help refine theoretical models of relativistic jet production. Understanding the processes that efficiently channel accretion disk energy into tightly collimated, relativistic jets involves complex magnetohydrodynamics and particle acceleration physics. Observational constraints derived from these quasars thus contribute to broader knowledge of relativistic astrophysics applicable across diverse cosmic phenomena, from gamma-ray bursts to active galactic nuclei. In sum, these exceptionally luminous objects stand as invaluable astrophysical laboratories. They challenge existing theories, inspire innovative methodologies, and dramatically enhance our understanding of fundamental physics, cosmic evolution, and the early universe. Delving deeper into astrophysical theory, hyperluminous quasars compel researchers to re-evaluate the initial mass function, IMF, and star formation rates in the primordial universe. The rapid buildup of supermassive black holes demands either an unprecedentedly dense environment rich in gas, or significantly higher stellar densities, potentially indicating shifts in early universe physics or previously unknown mechanisms of star and black hole formation. Additionally, the physics of accretion disks under extreme gravitational conditions remains an area of ongoing exploration. Current simulations indicate that the accretion disk around an ultrabright quasar might transition into an advection-dominated accretion flow, ADAF, in which a significant portion of gravitational energy is absorbed directly into the black hole rather than radiated away. Investigating ADAFs in such extreme contexts could uncover novel accretion dynamics and energy dissipation mechanisms, bridging theoretical gaps between classical accretion models and more complex relativistic disk behaviors. Studies of quasar-induced winds also provide critical insights into kinetic feedback, an essential ingredient in cosmological simulations that dictate the evolution of galaxies. In these hyperenergetic environments, kinetic outflows, streams of gas expelled by intense radiation pressure, carry metals and other enriched elements far into the intergalactic medium, IGM. Understanding this process enables cosmologists to refine numerical simulations predicting galaxy-scale metal distribution and evolution, illuminating the cosmic pathways through which life-essential elements disperse across vast cosmic distances. Moreover, luminous quasars indirectly facilitate the study of large-scale cosmological structure. As light emitted by these quasars travels immense distances, subtle distortions caused by the gravitational fields of intervening galaxy clusters provide precise tests of general relativity on cosmological scales. Such measurements can potentially identify discrepancies or confirm alternative gravitational theories, offering astronomers critical empirical tests beyond local environments. Additionally, quasars of extraordinary brightness may serve as reference sources in precision astrometry, the accurate measurement of cosmic object positions. By tracking minuscule positional changes over decades, astronomers aim to detect subtle relativistic phenomena such as gravitational waves, black hole binary interactions, or even microlensing effects at extreme cosmological distances. These positional observations could lead to breakthroughs in our understanding of cosmic gravitational wave backgrounds and the evolution of supermassive black hole binaries. Ultraviolet and X-ray emissions from quasars also deeply influence intergalactic chemistry. Photons emitted by the quasar ionize surrounding gas, fundamentally altering its chemistry and thermal structure. Detailed observations enable astrophysicists to map the distribution of highly ionized elements like carbon, C4, oxygen, O6, and neon, Na8, thus shedding light on the temperature and density distribution of diffuse cosmic gas, vital components in cosmic simulations of structure formation and evolution. From a broader theoretical standpoint, the observed abundance of extremely bright quasars at high redshift poses challenges for cosmic inflation models and structure formation timelines. Standard cosmological simulations must either account for earlier formation times of large-scale structures or reconsider assumptions about initial density fluctuations shortly after the Big Bang. Such insights could ultimately reshape the theoretical framework of cosmological history. Furthermore, observations of hyperenergetic quasars serve as laboratories for plasma physics, including processes such as magnetic reconnection, an important mechanism in particle acceleration and jet launching around compact objects. Detailed analysis of emission variability patterns and polarization signatures provides clues about how these magnetic processes unfold in extreme astrophysical environments, advancing our understanding of high-energy astrophysics and plasma dynamics more generally. Finally, these luminous cosmic beacons offer opportunities for multidisciplinary studies involving nuclear physics, particle physics, and quantum field theory. Observations of intense gamma-ray flares, neutrino emissions, and relativistic particle jets enable physicists to study particle acceleration, quantum electrodynamics, QED, effects in strong electromagnetic fields, and possibly even probe new physics scenarios like axions or dark photons, hypothetical particles proposed by theories beyond the standard model. Thus, beyond their astronomical interest, extraordinarily luminous quasars hold immense potential to revolutionize numerous branches of physics, fostering deeper insights into fundamental cosmological phenomena, particle physics, and the universe's earliest phases. The study of exceptionally luminous quasars also advances our understanding of radiation-driven accretion disk instabilities. In such intense environments, radiation pressure can exceed gas pressure by orders of magnitude, potentially triggering instabilities like the thermoviscous or photon bubble instabilities. These phenomena may cause the disk to fragment into dense, radiatively opaque clumps or induce rapid fluctuations in luminosity and disk structure, observable through precise photometric monitoring. Moreover, detailed analyses of luminous quasars' multi-wavelength emission patterns, ranging from radio to gamma-ray frequencies, enable astronomers to model the interplay between synchrotron radiation, generated by relativistic electrons spiraling in magnetic fields, and inverse Compton scattering, where photons gain energy through collisions with high-energy electrons. Studying how these processes balance each other provides deeper insights into particle acceleration and cooling mechanisms under extreme astrophysical conditions. Hyperluminous quasars also provide critical observational constraints on the opacity of the intergalactic medium at high redshifts. As photons traverse vast cosmological distances, interactions with neutral hydrogen and helium produce characteristic absorption features, particularly the Gunn-Peterson trough, valuable for dating the epoch of reionization precisely. Thus, these quasars are crucial cosmic chronometers that calibrate cosmological models concerning the universe's transition from neutrality to ionization. Additionally, quasars emitting exceptional luminosities challenge theoretical models of dust survival. Standard theories suggest dust should be rapidly destroyed by energetic photon fields, yet dust remains present in these extreme environments. Resolving this paradox involves re-evaluating dust grain growth, destruction processes, and radiation shielding mechanisms, potentially revising our understanding of grain physics and chemical enrichment at early cosmic epochs. Another intriguing area influenced by such powerful quasars is the study of starburst-quasar interactions. Astronomers hypothesize a feedback loop in which rapid star formation, starbursts, in the host galaxy fuels the quasar, while the quasar subsequently suppresses star formation through intense radiation-driven outflows. Observations of gas motions, star formation rates, and molecular gas distributions surrounding these hyperenergetic cores help refine feedback models, clarifying the coevolutionary relationship between galaxies and their central supermassive black holes. The extreme brightness of distant quasars also allows astronomers to probe previously inaccessible cosmic epochs, notably within the epoch of first galaxies, the period when the earliest galaxies assembled. By illuminating these early galactic structures, the quasars provide information about primordial star populations, population 3 stars, the formation of initial galactic clusters, and dark matter halo growth at unprecedentedly early cosmic times. On the experimental frontier, future gravitational wave observatories, such as the Laser Interferometer Space Antenna, LISA, aim to detect gravitational waves generated by supermassive black hole mergers involving luminous quasars. Correlating gravitational wave events with electromagnetic signals from these quasars could confirm models of black hole growth, accretion dynamics, and merger-driven galaxy evolution scenarios, profoundly influencing gravitational wave astronomy. Additionally, studies of hyperluminous quasars yield insights into cosmic magnetic field evolution. Their strong polarized emissions indicate organized magnetic fields at extraordinary strengths, influencing accretion dynamics, jet collimation, and particle acceleration. Understanding these fields' origins and evolution is pivotal for comprehensive models of galaxy formation and magnetogenesis in the universe's infancy. Moreover, the extraordinary radiation fields produced by these quasars help astrophysicists test quantum electrodynamic (QED) processes in intense gravitational and magnetic fields. Phenomena such as vacuum birefringence, where the vacuum itself behaves like a birefringent medium under extreme magnetic conditions, might become observable, allowing unprecedented tests of fundamental physics. Lastly, hyperenergetic quasars indirectly support cosmological studies of cosmic ray propagation and high-energy neutrino sources. The acceleration processes and extreme energies inherent in these quasars make them ideal laboratories for particle acceleration physics, potentially identifying distant sources of ultra-high-energy cosmic rays, UHICRs, and neutrinos, bridging astrophysics and particle physics into a coherent observational framework. Therefore, studying such exceptionally luminous quasars not only enriches astrophysical theory but also holds the promise of answering some of the universe's deepest scientific questions, connecting cosmology, fundamental physics, and early universe astrophysics into a unified scientific narrative. Exploring these enigmatic cosmic beacons pushes the very boundaries of human knowledge, provoking deeper inquiries into the fabric of reality itself. Their extreme luminosity hints at unseen processes lurking beneath the observable physics, compelling scientists to consider new and exotic mechanisms, perhaps phenomena linked to dark matter, dark energy, or hidden extra dimensions. Could these objects, shining more intensely than entire galaxy clusters, be subtle gateways to undiscovered physical laws or cosmic realms we have yet to fathom? Intriguingly, the immense gravitational pull of these quasars could also enable astronomers to test ideas about the holographic principle, a speculative yet profound theory suggesting that information about our three-dimensional universe may be encoded on a two-dimensional boundary surrounding black holes. Observations of subtle quantum or gravitational phenomena in such intense environments might someday unlock clues about how space, time, and gravity intertwine at the deepest quantum scales, possibly bringing scientists closer to solving the long-standing puzzle surrounding black hole singularities. Moreover, the extraordinary particle acceleration environments found near these luminous giants might shed light on mysteries of cosmic rays, neutrinos, and dark matter annihilation signatures. Could the quasar's vicinity, bathed in intense radiation and powerful magnetic fields, be a natural accelerator far surpassing any human-made collider? Could subtle signals in its spectra or cosmic ray fluxes observed on Earth hint at interactions involving undiscovered fundamental particles? Additionally, cosmologists speculate whether luminous quasars from the early universe hold hidden clues about cosmic inflation, the brief but explosive expansion following the Big Bang that shaped the universe as we know it today. Subtle patterns imprinted in the large-scale distribution of such quasars could provide observational signatures of inflationary physics, offering critical tests for theories currently constrained to theoretical speculation. Astrobiologists also ponder the indirect implications of hyperluminous quasars for the possibility of life elsewhere in the universe. While their intense radiation might sterilize nearby planets, could their powerful outflows distribute essential elements such as carbon, oxygen, and phosphorus, seeding distant galaxies with the building blocks of life billions of years before Earth formed? Are these extraordinarily bright objects, paradoxically destructive at close range, vital participants in cosmic chemical cycles essential for life's universal emergence? Equally compelling is the possibility of using these quasars as standard beacons, cosmic lighthouses whose predictable luminosities across vast cosmological distances could refine precision cosmology beyond current capabilities. Could detailed measurements eventually reveal subtle deviations from the standard cosmological model, pointing astronomers toward new forms of dark energy or previously undetected spatial curvature? From a more speculative standpoint, the mind-boggling energies involved near these quasars ignite imagination about unknown astrophysical phenomena. Could their gravitational fields twist spacetime enough to form transient wormholes or exotic gravitational lensing patterns? Might these luminous behemoths host unimagined astrophysical entities, like exotic compact objects, boson stars, or hypothetical cosmic strings passing close by, leaving discernible signatures for careful observers? Ultimately, such hyperluminous quasars symbolize humanity's relentless quest to comprehend the cosmos at its most extreme. As astronomers continually refine their instruments and techniques, these powerful celestial beacons promise discoveries that not only enhance astrophysical understanding but also potentially reshape fundamental conceptions of reality itself. Every observation thus becomes a thrilling step toward decoding cosmic mysteries that have tantalized thinkers since time immemorial. Beyond their scientific significance, these extraordinarily luminous quasars serve as profound reminders of nature's ability to surpass human imagination. They challenge scientists to venture beyond established theoretical frameworks, urging the exploration of radical new hypotheses, such as quantum gravity effects near singularities, alternate formulations of spacetime geometry, or unconventional dark matter properties. Could the spectacular luminosity and rapid growth of these supermassive black holes signal interactions with previously undetectable fields or dimensions of reality hidden from our current perception? Astrophysicists also speculate about observational signatures that may emerge from quasar mergers, rare, violent events expected to shake the fabric of spacetime itself. Such titanic encounters, involving the collision and eventual unification of billion solar mass black holes, could emit gravitational waves detectable by next-generation detectors. Could detailed electromagnetic observations correlated with gravitational wave signatures revolutionize our understanding of gravity, confirming or disproving alternatives to Einstein's theory. Additionally, theoretical physicists explore how hyperluminous quasars might illuminate deeper insights into entropy and information flow within the cosmos. The intense energy transformations occurring near the black hole event horizons of such objects provide unprecedented natural laboratories for testing concepts tied to black hole thermodynamics, the holographic encoding of information, and even the subtle interactions between gravity and quantum information theory. Could detailed study of these quasars eventually resolve the black hole information paradox, one of physics' greatest unresolved mysteries? From a cosmological perspective, the most brilliant quasars serve as powerful probes of universal homogeneity and isotropy, core assumptions underpinning cosmology. Detecting even slight irregularities or directional anomalies in quasar distributions across cosmic distances might hint at large-scale cosmic anisotropies or deviations from standard cosmological assumptions, potentially leading to paradigm-shifting revisions of cosmological theory. Moreover, the remarkable stability and visibility of hyperluminous quasars over billions of years raise intriguing possibilities in observational astronomy. Their enduring brightness over cosmic timescales allows astronomers to compare ancient radiation patterns with modern observations, potentially identifying subtle cosmic variations, such as drifting fundamental constants, changing physical laws, or evolving dark energy properties. Could these quasars be cosmic benchmarks, tracking the universe's evolving nature across immense stretches of time? Furthermore, the interplay between hyperluminous quasars and their host galaxies opens tantalizing possibilities about galaxy formation and evolution processes. Understanding how such incredibly energetic objects impact star formation rates, galaxy morphology, and interstellar chemistry deepens our insight into galaxy-quasar coevolution. Could quasars of such staggering brightness fundamentally shape galactic destinies, regulating cosmic cycles of birth, destruction, and renewal across eons? Even more provocatively, some physicists consider whether the most luminous quasars might shed observational light on exotic cosmological objects such as primordial black holes, hypothetical remnants from the Big Bang itself. Could tiny primordial black holes, captured into orbit or consumed by these colossal supermassive black holes, leave detectable imprints within quasar radiation or gravitational wave emissions, revealing insights into conditions mere fractions of a second after the universe's birth? Ultimately, luminous quasars represent a cosmic frontier whose exploration may forever alter our scientific understanding and philosophical outlook. Their extraordinary properties pose fundamental questions. What unknown physical laws await discovery within their turbulent hearts? Are there entirely new forms of matter or energy operating in these extreme environments? Could studying these cosmic giants provide humanity with profound new insights into our own existence and place within the universe? In pursuing these celestial enigmas, astronomers embark on one of humanity's most thrilling intellectual adventures, pushing boundaries, inspiring innovation, and transforming our understanding of the universe, from the smallest quantum scales to the cosmic expanse itself. Exploring the depths of these radiant cosmic powerhouses may eventually unravel mysteries surrounding cosmic acceleration and the enigmatic nature of dark energy. Their luminosity and clarity at immense distances offer an unparalleled tool to precisely map the universe's expansion history. By meticulously charting luminosity variations across cosmological scales, astronomers might detect faint signals or anomalies pointing to undiscovered components influencing cosmic evolution. Could subtle patterns hidden within the radiation of these extraordinary quasars hold the key to solving the greatest cosmological puzzles of our age? From a gravitational perspective, superluminous quasars present tantalizing opportunities to investigate possible deviations from Einstein's theory of general relativity. Their intense gravitational fields and relativistic environments create ideal testing grounds to measure subtle effects predicted by modified theories of gravity, including scalar tensor theories or higher dimensional models. Could precise observations of emission lines or relativistic jets near their central engines ultimately provide empirical evidence supporting revolutionary new theories of gravity and spacetime? Moreover, the magnetic field structures and plasma behaviors surrounding these luminous giants open windows into plasma physics regimes unattainable in terrestrial laboratories. Observations of coherent electromagnetic flares, magnetic reconnection events, and particle acceleration near these cosmic dynamos offer astrophysicists a chance to better comprehend fundamental magnetohydrodynamic processes, which govern phenomena as diverse as solar flares, cosmic ray acceleration, and pulsar wind nebulae. Could detailed quasar studies fundamentally enhance our knowledge of plasma physics, guiding breakthroughs across multiple scientific disciplines? Equally intriguing is the possibility that supermassive, hyperluminous quasars may indirectly inform searches for extraterrestrial intelligence. Though their intense radiation might render nearby regions hostile to life, their visibility and recognizable radiation signatures across billions of light-years may serve as universal markers or cosmic beacons recognizable even by distant civilizations. Could such phenomena play roles in interstellar communication strategies or serve as natural reference points in hypothetical extraterrestrial navigation? Additionally, theoretical cosmologists propose that such extreme environments might harbor novel quantum gravitational effects observable through distinct spectral signatures or polarization anomalies. Intense gravitational fields near quasars' event horizons could amplify minuscule quantum-scale phenomena, making them detectable over cosmic distances. Might careful scrutiny of these spectral fingerprints uncover direct observational evidence for elusive quantum gravity theories, merging quantum mechanics and general relativity into a unified description of reality? Even more speculative theories suggest that ultra-bright quasars could be sites of transient spacetime anomalies, such as hypothetical microscopic wormholes or quantum black hole fluctuations, due to extreme gravitational and quantum conditions. While firmly rooted in theoretical physics and highly conjectural, detecting any indirect observational evidence of such exotic phenomena could revolutionize physics and cosmology, opening unprecedented paths toward understanding the nature of spacetime and quantum interactions. From an observational strategy perspective, future telescope arrays combining extreme precision interferometry, adaptive optics, and next-generation X-ray observatories might achieve unprecedented resolutions. Such technologies would enable astronomers to image quasar accretion disks directly, revealing dynamics previously hidden within observational uncertainty. Could future instruments peer so deeply into these luminous hearts that we directly observe matter spiraling into black holes, witnessing first-hand phenomena previously accessible only through indirect inference? Furthermore, luminous quasars may help astronomers identify intermediate mass black holes, IMBHs, long hypothesized yet elusive black holes bridging stellar mass and supermassive regimes. Interaction or mergers involving these intermediate mass black holes near hyperluminous quasars might produce unique electromagnetic and gravitational wave signatures, facilitating their long-awaited detection. Might quasars serve as critical observational gateways toward finally confirming IMBH existence and solving key questions surrounding black hole population growth across cosmic time? In essence, each luminous quasar symbolizes an astrophysical laboratory, a cosmic particle accelerator, and a gravitational experiment rolled into one. Their continued exploration fuels humanity's innate drive to understand nature's extremes, continually reshaping our intellectual landscape. As astronomers delve ever deeper into their secrets, luminous quasars promise discoveries not merely incremental but revolutionary, transforming our scientific worldview, enriching our understanding, and continually igniting wonder at the marvels of the cosmos. Ultimately, the exploration of these luminous cosmic titans exemplifies humanity's relentless quest to comprehend nature's most extraordinary phenomena. With every observation, astronomers step closer not only to decoding the astrophysical mysteries these quasars present but also to potentially uncovering entirely new physical laws and cosmic realities. Each discovery pushes the frontiers of human knowledge outward, challenging our theoretical frameworks and reshaping our understanding of the universe, from its earliest moments after the Big Bang, through the intricate evolution of galaxies, down to fundamental quantum scales. In studying these hyperluminous quasars, we confront the profound beauty and complexity of our universe, reminding ourselves that what we currently understand is but a fragment of a greater cosmic narrative waiting to be unveiled. They stand as celestial monuments, testaments to nature's extremes, continually inspiring scientists to pursue new insights, forge innovative instruments, and advance revolutionary theories. As future generations of telescopes and space observatories continue to peer into the distant reaches of space and time, luminous quasars will remain among the most compelling targets of astronomical inquiry, ever guiding humanity onward in our eternal quest to illuminate the unknown.